Welcome to this session on classification trees. Today, we'll dive into decision trees specifically designed for categorical outcomes, often referred to as classification trees. We'll explore how they work, why split points matter, and how metrics like the Gini index optimize decision-making in these models. A classification tree is a type of decision tree where the target variable is categorical. It uses a process called recursive partitioning to split data into purer subsets. For instance, if a target variable is binary, subsets become purer as cases group into similar classes. Let's consider impurity. It's highest at 50/50 splits and decreases as groups become homogeneous. Identifying the best split points minimizes impurity, optimizing predictions. We will refer to the HELOC case in the textbook. Let's practice determining possible split points of the income variable. To calculate possible split points, we first organize the data in ascending order, and then we take the average for each pair of consecutive data points. For example, the first split point in the data set presented here is the average of 4,000 and 11,000, which is 7,500. Determining possible split points for classification trees is a pivotal step in crafting an effective decision tree model. But why are these split points so critical? Let's explore. First, split points play a major role in improving predictive accuracy. By dividing datasets into homogeneous subsets with shared characteristics, split points allow the model to predict target variables with higher precision. Next, split points simplify the complexity hidden within data. They enable the model to unravel intricate relationships that aren't immediately apparent, effectively capturing patterns that would otherwise be missed. The goal of splitting is to minimize impurity in the resulting nodes. Metrics like the Gini index or information gain guide the model in choosing the most effective splits, resulting in more distinct and pure child nodes. Split points also enhance the interpretability of decision trees. Each split represents a clear decision rule, making it easier for stakeholders to understand and trust the decision-making process, a critical factor in business contexts. Lastly, determining the best split points optimizes decision-making. For instance, in marketing, these splits can identify distinct customer segments, enabling tailored strategies that drive results. In summary, split points are the backbone of decision trees, improving accuracy, simplifying complexity, reducing impurity, enhancing interpretability, and empowering smarter decisions. The Gini index, also referred to as Gini impurity, is a crucial metric used in evaluating the performance of classification models, particularly in decision tree algorithms. It quantifies the frequency at which a randomly chosen element would be incorrectly labeled if it were randomly assigned based on the distribution of labels in the dataset. The Gini index ranges from 0 to 0.5, with each value indicating a different level of classification purity. A Gini index of 0 signifies perfect classification where a node is entirely pure. Conversely, a Gini index of 0.5 indicates that elements are randomly distributed across various classes, representing an impure node. The Gini index formula is presented here. It represents the ratio of all cases that belong to the target class to the total number of cases. Let's practice calculating the Gini index using some examples. The index is 0 if all cases belong to one class. The index is 0.18 when 90% of cases belong to one class. Lastly, the index is 0.5 when half of the cases belong to each class. As depicted in these examples, the best split point is the one that produces the smallest index value. Let's look at an example from the textbook. The HELOC introductory case contains information on income and age for banking customers who receive a HELOC offer. The blue points represent customers who did not respond to the offer. They are class 0. The orange dots represent customers who did respond. They are target class 1. With no predetermined split value, we simply count the number of points for each class and across both classes. Our result is a Gini index of 0.3759. Next, let's look at using split values. When we split on the age variable at a value of 49, we again count the points in each class and across classes for each side of the split point. The result is 0.25, which is better than no split point, but there are no pure subsets at an age split value of 49. What if instead we split on the income variable? Using a split value of 64,500, we arrive at an index value of 0.2727, which is better than no split value, but not as good as the 0.25 value we saw when we split at age 49. This means we would choose age as our root node for the decision tree. Once the root node is established, we then calculate the probability of an observation belonging both to the target class and belonging to either side of the split value. We can have multiple split values for multiple variables. In this figure, we can see 2 split values for age and 4 split values for income. The split lines are plotted on the left. Arrows are provided to show how these split values are charted in the decision tree. A large data set with many predictor variables will likely generate a very complex tree. As the number of partitions increases, the misclassification rate from the training data set will decrease eventually to 0. For a new dataset, validation, the misclassification rate will likely decrease initially but increase after a certain point due to overfitting. Pruning is an important step to optimize the complexity of the final decision tree. A simple approach to prune a classification tree is to reduce the misclassification rate in the validation data set by replacing a branch of the tree with a leaf node. Going back to the HELOC example, we take a small sample of 5 records to demonstrate simple pruning. Here, the age 23.5 branch is replaced with a leaf node. This prune tree accurately classifies all 5 records. The 2 records under age 49 did not respond. The 1 record over age 49 with income less than $39,500 did not respond. The 2 records that were above age 49 and had income above $39,500 did respond. Let's practice building a classification tree in JASP. First, load the travel file from the resources section in this module. Then select Machine Learning, Classification, and Decision Tree. Next, move the selected variables into the Features box as depicted in the screenshot. Then select the table options, Data Split Preferences, and Training Parameters as indicated here. Our results window shows that our classification tree has 71% accuracy. 2 variables can serve as possible splits for the tree. We use Credit Card because it has the highest improvement. Our tree results in 3 leaf nodes. You can check these answers against the answers given in Application 13.12 in the textbook at the end of the chapter. Please note these are the only values that will align with the textbook answers. JASP uses a different version of R than the text, so the remainder of the metrics will not align. Thank you for your attention. This concludes our lecture on classification trees.